Okay, welcome everyone to the Science Chat, and I am your host, Franklin Hu, and today is July 14th, 2018, and this is sponsored by the John Chappell Natural Philosophy Society, and you can come visit us at our website, naturalphilosophy.org, and you can become a paying member of our membership, and you can find us at forums on naturalphilosophy.org and on Facebook. Okay, so today is kind of an open discussion, and we are going to be switching over to something called Easy Talks, since for some reason Fuse has decided to shut down inexplicably. So let's see here. I believe I have their website here. So this is www.easytalks.com. So probably it's going to be the same deal where we just give you a link. You can probably go to this website. I'm not sure whether it's going to be needed to sign up just to join a meeting. I'm imagining probably not, but you can do that if you want to start experimenting around, and you can perhaps download their software if they have any. So that's just a heads up. We'll probably be switching to that soon. Probably August 4th. We'll definitely be switched over. Okay, so we were discussing a little bit about banning people from the conference. So Pal, what did you have to say about, what is your opinion on things like that?
I agree with you 100%. I think it's a badge of honor to be controversial.
Yeah, I think that's true. I think the purpose here is to be controversial. I think the goals of our group are to make sure that there is a place where people can voice their opinions. I think in this case, though, it was just that that Draft Science, had said some things which were critical of the organization, and not necessarily even something related to science. But I think we should be open to people who are perhaps critical of us, even if we don't like it, because if you always just shut down the people who are critical of your opinions or your group, then you are enforcing this kind of mono thinking, I think, and then you would never, they could have valuable objections and legitimate objections, but if you just choose to get rid of those people, then I don't think you would ever learn. I mean, and I think that especially for a group like ours, where we're trying to question basic science, that we do need people who, even though they might seem a little unruly at times, they need to be there to challenge us so that we realize what our basic assumptions are, as oftentimes we really don't. So, for example, last week, the whole question of whether positrons existed was brought up, and for me, it's like, I would probably never really question that, but that someone comes up and begins to question that means that we have to go and actually show that our primary assumptions, such as things like positrons exist as unique entities, can actually be backed up.
More than that, Franklin, I think I go a step further. I would say that anybody should be free to discuss their feelings, their disagreements on any matter that's on their mind. It doesn't have to be science, and it may not even be considered a chat. It may be even considered somewhat rude. But that's where you step in, where the moderator has, you know, considerable flexibility to make those decisions as to what is really a proper role of moderator. Where does proper science chat end and rudeness begin?
Yeah, that is one of the roles that like, for example, I feel it's like if we were to ban someone from our group here, that would have to be a decision that I would have that I would make, really. Because I would only ban someone only if they were deliberately abusive or I couldn't control them at all. So, and I don't think draft science reached that point. It's a little bit challenging to make sure that we don't repeat the same argument over and over again. And I will step in there to make sure that the conversation moves forward. But that's my challenge, and that's my position and job as moderator, to make sure that we are sticking to the topics, not jumping way too far off on things which may not have to do with physics, or make sure that people are treating each other with collegiate respect.
Yeah, and I would even say that in the mix, we should also keep in mind that, and you should particularly keep in mind, that the powers that be should always be respected, regardless of our personal opinions. Now, in this case, I think the main power behind this is our leader, not of Science Chat, but the whole organization, CNPS, which is David Alistair. And I'm, for one, very thankful to him, all the work he has done, not only on behalf of CNPS, but also its predecessor organization, NPA, for many years before that, even though there were a few years where he was kind of taking a short break or breather and re-evaluating the mission of the NPA and getting a big flack from the organization that basically took over the NPA name. And then somehow CNPS was born, and everything has been peace since then. That's my 2 cents worth.
All right. Well, hopefully we won't be banning any other people, and maybe I'm hoping that the leadership will reconsider, since I think that draft science was adding a lot of interest to the discussion group. And one of the things that I find most difficult in moderating this discussion group is actually getting people to talk. So I thought he is so losing him is not something that I want to have happen. So okay, so in any case, so I was wondering, does anybody have any particular topics that they want to discuss before I get into what I was going to show, which is this website called Glaze Labs. So we have some people. So this is your chance. You speak out. You guys got a topic? Let's see here. I hear silence. So does that mean you all want to learn about what's on Glaze Labs website? I see we have some people but don't have microphones, like Jim and Mitch. Okay, well, it must be that you want to go see what's happening on this website. It's called Glaze Labs. So let me give you the 2-cent tour here. Okay, so you guys see my screen?
Glaze
Someone say yes.
Yeah, I see it.
Okay, so this is the website of Glaze Labs Research. So in lieu of getting people to talk, I'm just going to pick somebody else's website, and we're gonna go ahead and talk about what's there. So this website has been around for quite some time, and it's largely the work of where's his name here? Let's see, who's the contact here? Yeah, Glaze Labs Research at gmail.com. So if you want to contact the author, there's his email. What's his name? His name is like Xavier or something like that. Most of these articles are published by Xavier Borg of Glaze Labs Research. So he's got a lot of interesting stuff. His website is probably one of the largest influences on my own thoughts on things. Though primarily, one thing that's interesting about his websites is this what's called EHD Thrusters. And these are commonly known as lifters. So let's see here. I have got a short video here that shows these things. You guys probably can't hear the audio. So this is what these lifters look like. They're very simple. This is basically a balsa wood frame with toothpicks on each of the corners. And then on the bottom, you wrap the bottom with an aluminum foil. And on the very top is a very, very thin wire. So that's what the completed lifter looks like. So, pretty much anyone can make one of these things. The hard part is to get a hold of a 25 kilovolt power supply. Now, it looks like this guy has made one out of a old monitor board here. So you can build one of these things. So when you energize it, this thing just lifts off the ground, as you see here. And it does so quite rapidly. When you energize this thing, it just leaps off the table. So this is quite remarkable. So Glaze Labs, they have all kinds of information on people building larger versions of the things, on how much payload they can carry, and various other things here. Okay, so you guys were able to see that video? Someone say yes.
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 Okay, great. So, there's some controversy over how these things work. So, there's this really gigantic ones that they've built. And I think originally, there's some question about what is the mechanism here. Now, it's well known that you get what is called an ionic wind off of these kind of devices. So they feel that the main propulsion activity is due to this device basically kicking ions down from one part of the device, which is the thin discharge wire, to the very large collector, which was the aluminum foil part that you saw. And if you've ever observed the ionic wind, it does create literally a blowing wind kind of thing. Now, for me, from watching those videos, I just found it a little a little hard to believe that these things are generating that kind of thrust. Because you see it rise off the table so rapidly.
It's not a very big thrust in the sense that it moves much weight. It's very lightweight.
This is extremely lightweight, but it moves extremely quickly, almost kind of out of control. Although now in reading his current website, you know, they're showing some other early attempts to create these kinds of EHD thrusters. There's a picture of some Brown and Branson design. And there's some discussion about NASA tried to develop these things here. And there's a description. See, here's one that apparently can lift 100-gram payload here. Very large. And they have ways to optimize these lifters. So the question was, you know, as far as NASA is concerned, you know, will these things say work in space under a hard vacuum? So he has this whole page where they did their own experiment in a very hard vacuum. And their conclusion was that no, these things don't work under a hard vacuum. And it looks like they have this graph here, which shows basically that I think over on the right, you know, this is full atmospheric pressure, showing the air dielectric strength. And so as you pump out the air, as they move to the left, the green to like these purple dots, you get into this corona discharge zone here, which is in blue, where basically it's shorting out. But as you pump out the rest of the ions, then the air dielectric rises again. So that if you figure that it was that the effect was due to the dielectric strength, then it should regain its propulsive effect. But their conclusions was that after going down to hard vacuum, that the result of the experiment was zero thrust. So, and that this definitely confirms that the main lifter thrust is an electrohydrodynamic form due to ion interaction with neutral particles, and disproves once and for all any anti-gravity theory. Although I think this really never had anything to do with anti-gravity, even if it did work, because these thrusters would work if you placed them sideways. So it's a propulsion effect in any case, and not really an anti-gravity effect. But once again, I find that just a little bit hard to believe that it's fully that. But those are the conclusions that he has on the website. So did anyone have any comments about that?
Yes, I'd like to make a comment.
Yes, pal.
About what's in a name. Why do we attach so much significance to a name when we also know a rose is a rose is a rose by any other name too? So
what name are you referring to?
Or levitation or lift or magnetic or whatever doesn't really matter, as long as we understand it by whatever name they want to use for it.
Well, what name do you think is being used here that's of interest? The name lifters, or? How about Bill? Did you have a comment? Did you want to make about this lifter technology?
Did they show the range, or how high could they make it go?
How high they can get these things to go?
Yeah.
No, I don't think so, because generally speaking, you need a high voltage power supply, and I think it's kind of hard to make one of those such that it weighs less than the carrying capacity and still be portable. So generally speaking, these things have to be tied to the ground by a wire that's supplying the high voltage. So, and I've never seen these things get higher than like waist level. Just as a practical matter.
Yeah, so it's some kind of electrical effect that is fairly weak, and it wouldn't work on a heavy item, just on something real light with tinfoil and toothpicks and stuff like that.
Yeah, that would seem to mean the main problem. I mean, they have built, like I said, on this website, you see examples of larger lifters, but I imagine that would require larger power supplies, and to the point where it wouldn't be able to get off the ground. I mean, it would be kind of interesting to see one of these things actually levitate without any control wires. But I think the other problem with this kind of lifter is that it's pretty much out of control. And I've seen these lifters in videos where they have like longer wires. Now, basically, when they rise up, they just gyrate around wildly. I mean, in the particular video that I showed you, it showed like it rose up and just stood there. But that's only because the wires are relatively short, and it was just basically pinned down. If you put longer wires, I mean, this thing is just like it would not be stable at all. So that would be the other problem, that even if you were able to come up with a power supply strong enough to lift its own weight, that it would just be wildly out of control. That would be a whole nother problem you would have to deal with in order to create a stable craft of this sort.
Well, our Air Force has some planes that can fly without a motor or a jet engine, and we use them for ones that fly a long time, like all the way around the world, without having to be refueled. But they have to use fuel to take off, and they use fuel to land. But other than that, they can just cruise. And so there are some effects that are electromagnetic that help to defeat the force of gravity on big items that are very heavy. And but this is something different from that.
Well, there is this book, Secrets of Anti-Gravity, that I have read, which makes some kind of similar claims. For example, they actually claim that the B-2 bomber actually uses some of this electrostatic technology to basically provide more lift than would be provided by just, say, the shape of the airplane itself, and that there's some evidence that the plane during flight is actually charged, and that's one of the secret black aspects of a bomber, which is actually in operational use.
Yeah, well, my son's in the Air Force, and he's a pilot, and there are planes that can fly around the world and consume no fuel. But they do require fuel to take off and to land. But they can cruise all the way around the world without consuming any fuel. And
not be in orbit?
They're not in orbit in space. They're flying at in the part of the atmosphere that planes normally fly. So there are some things that can be done, and but they don't require. They're kind of like what you would call jet planes, but they can turn the engine off after a while and just keep on cruising. And but that's a secret. So they don't.
Yeah, that's a secret. I bet the commercial airlines would like to have something like that, where all you have to do is just have fuel to get your plane in the air, but once you're cruising across the United States, you don't have to use any more expensive fuel.
Well, I was involved with a group that was working with Winston Bostic, and they were based at MIT, and they modified a jet plane to use what we would call a soliton, an electromagnetic field, and which have tremendous lifetime and that sort of thing. And they
well, is that this? Do you think that's the same technology that this space plane uses? Because I've heard of this your story before about the soliton.
No, that's not
plane.
what I was wanting to point out. Was the commercial airlines, the Air Force, and NASA refused to use it because they couldn't make enough money for the individuals who worked in those organizations to get rich.
Is that the same technology? You think that's being used?
No, it's a different technology.
Different technology.
Yes, but what I'm saying is they were not interested in it because they couldn't justify spending millions or billions of dollars on it because they were showing a flight that cost less than $100 and it flew all the way around the world. And so they didn't like it. They wanted something that was much more expensive. Just like when I was working for the government and I invented the Supermicro computer, which was the world's fastest computer, and for 40 or 50 years, and it only cost $8,000, and they refused to buy it. And
so once again, it's like we have all this wonderful technology, but it's the oil companies and the people who build airplanes who are stopping us from getting this.
In this case, it's the people who work for the government. They want to give out multi-million or billion-dollar contracts because they get kickbacks on those. They don't get them if it's an $8,000 contract. You understand what I'm saying?
It's the man keeping us down, right?
Yeah, it's the people who want to benefit from the privileges of being in government.
Okay, but that's interesting to hear that, there is this possibility of having a plane which only requires fuel to take off, but under normal cruising conditions doesn't require any fuel. Yeah, that's the first time I've ever heard of something like that.
Yeah, it's only for cruising. It's not for taking off or landing.
All right. Well, just letting them know, people out there who might be watching this video, well, there's a possibility out there. Or either that Bill is making up stories, but, And I have no reason to think that Bill would deliberately make up stories.
The people who are promoting this new nanotech crystal for generating electricity, they would say if you had a plane that could run on electrical power, that this nanotech crystal would enable you to fly. Just like it's Tesla and Mercedes and quite a few companies have already made at least one car that runs on this nanotechnology crystal, and they've demonstrated it, and so people have seen it.
Yeah, but Bill, it's a big secret. The rest of us don't know about it. So.
It's on I get newsletters from the stock market all the time saying,
"Yeah, but those guys will say anything, and they usually do." Well, like I said, Bill, the day I get my cell phone that charges itself by the nanotechnology, I'll go, "Great, Bill's right the whole time."
Well,
and you say it's only a year from now, so we'll come back. I think 2019, and as a skeptic, I will predict that we will still have lithium-ion powered phones.
I'm hoping that we'll get that because I like to become energy independent.
Yeah, I would like that because charging your phone is just a pain in the butt, and there's no redeeming value to that.
Well, right? I don't want to have to pay for electric wires coming to my house. I don't want to have to pay a power company, or?
Well, definitely the power companies and the government will stop that. They'll definitely stop that. Bill, the problem is that if what you all say is true, then we'll never get our self-charging cell phone because of all of the terrible consequences to the people who earn their living of delivering us power. Now, I don't think the lithium-ion battery people have that much pull, but definitely the electric utility people would.
Yes, but like for instance, where I live, we have a co-op. And the co-op is providing our electric power. And so what we have is solar farms. And these farms get our electricity from sunlight. And so we use that in the daytime. At night, we buy power from power plants. But
yeah, so they're not going to let their gigantic multi-million-dollar investment go to waste because
well, see, my co-op has only invested in solar power, so they think that it won't hurt them if we could get something like a solar farm that works 24 hours a day, like this nanotech crystals might do, and then we wouldn't need to pay anything to a company that ran a power plant based on fossil fuels or nuclear power.
Well, I suppose they could build an industrial-sized power plant out of that stuff, and then they would still be in business. They'd still be able to sell you power and make money and keep themselves in business.
Yeah, but if I can buy one for myself,
even that would be a problem, right?
They wouldn't like that.
They wouldn't like that. If Bill can disconnect, can unplug and cut the cord from the power company, that would be very bad for the power company.
Yeah. Well,
so we'll see what happens there.
Yeah, I'll send you a link to what.
Yeah, you can send me a link. A link other than the stock market people where I have to send them $69.95 a month in order to figure out what this stock is, right?
Yeah, well, that's what it is. But anyway, the person who was testifying on this was a person whose job in Silicon Valley is to find the new startups that are going to make a lot of money, and so he claims that he can identify the technologies that are promising.
Unfortunately, though, if it was true, you would find that the inventor mysteriously killed and their lab burned down.
Well, you get to see a picture of the inventor and his name. You get to see demonstrations of the cars and stuff like that running on the nanotech.
And soon he will be mysteriously assassinated with his lab burned down, isn't it?
That's a possibility because there's a lot of people who have a lot at stake, unless they are investing also in this company. So what they're trying to say is the big companies, the people with wealth, are investing. Even people like Donald Trump is investing.
Or either that, it's all just a bunch of words on paper, but
we'll see.
We'll see. Let's see here.
In a few years, they claim most of the people in the world will get all their power from this type of a source.
Yeah, I'll have to just color me skeptical on that.
And the only resource they need is silicon sand to make it. And so the deserts of the world are now being bought because that's where the silicon sand is. Kind of like it's gold, they're buying it, but nobody appreciated it before, and so they didn't consider deserts valuable.
Okay, well, let's go look at some other stuff on Glaze Labs.
Yes.
It looks like they have an atomic model. Let me see here. No, this is something else. Let's see here. He has something about. I was just looking at this website. He's got something on particles here. We have a new proposed atomic model. So maybe, Bill, you might be interested in this. So but this appears to be a theory based on standing waves.
I don't know if you realize
So he has this.
My model, the toroidal ring model for the electron, there are two types of waves that can be standing waves in the toroidal ring. You can have one wavelength around the ring. That's what Arthur Compton and his graduate students worked with. Then you could have the circumference of the ring be two standing wavelengths, 3, 4, and 5. And when you make a transition, it's just like having power coming off of the antenna. You just drop from the 2 wavelengths down to 1, or 3 wavelengths down to 2, and so that way you get the emission, and you don't have to change orbits or anything like that. It's just a standing wave pattern in the actual shape of the toroidal ring. And but in addition to
let's see here. Well, this particular standing wave, so he has this wave structure of the particle. In particular, he has a mathematical proof that the electron is a spherical electromagnetic standing wave. So apparently he doesn't think it's a toroid. He thinks it's a spherical standing wave.
Well, that violates the laws of electrodynamics. So if you put any trust in the empirical laws of electrodynamics, it can't be a sphere. Because a sphere cannot have a magnetic moment and a spin moment.
But it might turn out that what you're measuring as a spin and magnetic moment aren't actually inherent properties of the electron.
Well, but they've been measured in the.
Yeah, it's true. You can measure properties of electrons.
You can put one electron in our devices and measure various properties of it, and you can measure its spin, its magnetic moment, its mass, all that kind of stuff, to high accuracy in these. It's a device where it just holds it stationary between electric and magnetic fields.
Yeah, but you say things like this violates the laws of electrodynamics, and it's like,
that's right.
Does it really?
The sphere does. The sphere does. We know that they're not spheres. We know by scattering electrons on one another they're not spheres, because they don't scatter like spheres scatter. They scatter like toroidal rings scatter. So, you've got to throw away all your empirical data and throw away your empirical laws of electrodynamics if you want to use a spherical model.
Well, you would have to show me the data, because I'm not aware of any experiments that show that the electron is non-spherical. All the mainstream evidence seems to indicate that they can't figure out any shape for an electron.
The mainstream avoids all the issue by having point particles.
Yeah, I mean, that's what they basically resort to. They basically say it's a point particle, and point actually has no volume. And therefore, it can't have any shape.
And it produces infinities, and they have to find mathematical tricks to get rid of the infinities.
But I would think that if there was I'm just questioning your assertion that there's experimental data to show that the electron has non-spherical shape. So I would have to be shown that. And so far, I've never seen any such evidence.
Well, you can scatter electrons on electrons, and you can see that.
No, I don't think you can. I think you scatter electrons.
At College of William and Mary, where I got my PhD, we did those experiments at the Space Radiation.
And what happens? I mean, even if the electron were non-spherical, you would get so much scattering at every possible direction that it would look spherical.
You can scatter one electron on one electron.
I mean, let's suppose the electron was in the shape of a bar, and then, if you shot 1 million electrons at random orientation against 1 million electrons of another random orientation, and if you were to look at the scatter from that, I would assert that the scatter would be indistinguishable from a spherical object because it would just be scattering off every possible combination, and it would come off in every possible direction.
We can scatter one at a time.
Yeah, even if you scatter one at a time, unless you can control what you think the orientation is. Otherwise, it's going to be like colliding two cars, and even though the car is this rectangular box thing, all the pieces that are going to fly out would be exactly the same as if the cars were spherical.
With electric and magnetic fields, we can change the orientation.
So that might be one possibility if you think you can if you can influence the initial shape, assuming that it's not spherical.
The electron cannot be spherical because it has a magnetic moment, and therefore that breaks the spherical symmetry and defines a definite axis to whatever the structure of the electron is.
Well, that's certainly, that goes to the experiment that actually measures that magnetic moment. Now, for those of us who are skeptics about that particular item, it's because the only way you can measure that magnetic moment is to put it in a trap where you get it to oscillate, which means it's moving. Now, that we know for a fact that moving electrons create magnetic fields. So I find it very difficult, unless you can measure the magnetic moment on a stationary electron. And I don't know how you would do that because a stationary electron doesn't emit anything that's measurable. I would assert that this is my criticism to these types of experiments, that you're not measuring something which is actually an inherent property of the electron. My criticism would be, I would assert that you are measuring a property that is actually being created by the circumstance of the electron in motion.
Well, if you have a trap and the electron is stationary, and you take a laser and you put energy into the electron, and it comes out, you make standing waves in the electron, and then that's emitted. You can measure that, and you can see that the electron's not moving. And so here you have fields being absorbed and emitted by something, which you call an electron. And we think only way that can happen is if it's in a shape like a toroidal ring of some sort.
Well, once again, I would have to be shown that experiment to see that whether it was really moving and what you were using to conclude that it was a toroid. See, these are all really indirect kind of evidences, and there's always a bias in these kind of things, that you may find what you're looking for if you look hard enough, if you cherry pick enough.
You can get it directly from the empirical laws of electrodynamics by solving the complete set simultaneously. In other words, you've got so many unknowns and so many equations, and what Oliver Heaviside did when he replaced Maxwell's quaternions with vectors is he threw away some of the equations, and he threw away the terms that he couldn't explain because he didn't have the complete set of equations. And
I'd like to speak on this subject when everybody's had their shot.
Go ahead.
If you solve it directly, Angel, you will get twice as many terms for the electromagnetic force, the most general form of it, than as you do from Oliver Heaviside's version of electrodynamics, which we call Maxwell's equations. And,
okay, go. Who wanted to speak?
Alistair.
Alistair. Okay, go ahead.
And sorry, I haven't been here for a while. In the theory that I proposed, and we talked about it in one session a few months back, I proposed that the medium that hosts reality as we experience it is made out of balls that have a sort of bi-semi-toroidal nature, which would allow things propagating through them to be spherical because the medium itself is the toroidal property of it. So you could get spherical waves that would still have a polarity to them because the polarity is given to them by the medium.
All right, I'm not quite sure I understand that, but getting specifically to the question is, what is the shape of an electron? So what do you think the shape of an electron is?
Spherical.
Spherical, okay. I think that's kind of the intuition, I guess, that most people have. Now, that could be totally wrong, but...
And toroidal.
And toroidal.
It flip-flops between them. So that the average is a sphere, but it's actually a toroid in motion.
Well, it could be. That was kind of my point, that no matter what shape the electron is, it's so tiny that if it has any kind of rotational ability, it's going to end up looking spherical. At least its field would be. I mean, not unless you can get it to like be in one specific position and then measure its properties.
If my model is correct, the electron is not an actual particle, it's a virtual particle. Kind of like if you had a bunch of dots and you connect the dots, so it looks like there's a sphere there, but really what you're doing is connecting a bunch of dots.
But then
so
you have
the
the problem
electron doesn't exist as a physical particle because the medium itself is the physical contribution. The electron is passing through the physical medium, so it adopts the nature of the physical medium. But to our perception, because we're also passing through the physical medium, the electron will be perceived as spherical because it and us are all passing through it at the same time.
But then you explain what the dots are.
I don't know if you would remember the picture of the shape that I propose as the root particle of the medium. I don't know the best way to transfer that picture.
Thing? Was that the red and blue ball thing?
Yes, exactly.
Okay, I remember that. Well, that still doesn't really explain what those things are. I mean, even if you call them red and blue, you still have to kind of explain what they are.
You have to be able to take a step back and stop thinking of the things that we perceive as being physical. You have to stop thinking of them as physical and recognize them as objects that are passing through the medium, and the entire medium is made of close packed red and blue balls. Well, would really help if I knew how to transfer the picture to you. So that
I remember seeing that. So, but anyone can imagine a close packed spheres. Anyway, so that's not a very complicated picture. I mean, that's not actually, say that much further away from my own preferred embodiment of space, except I just say that those red and blue balls are just positrons, electrons, really. So.
Right. So if
there's no mystery as to what those things are.
But if there's a medium that has just perfect regular spheres, the issue is that medium can't generate toroids because it's made out of just spheres. Where does the toroid shape come from? But
it doesn't, that would be my point. So
if the medium is made out of quadrupole, I guess they're closest to quadrupoles because it's like two dipoles, but they're flipped in half and the halves are inverted. Then the average of them passing from one to the other creates the toroid, and then the average of the toroid, when you see it from the bigger perspective, is a sphere.
I don't know. I don't think you can take two shapes and take the average, generally speaking. It's not like numbers where you can take the average of numbers. if you take the average of a square and a triangle, you know, what is that? You know,
But you can do that.
I would kind of disagree. I mean, I don't know what shape you would come up the average of a square and a triangle would be. But I'm just saying that's kind of a weird concept. So
It's not straightforward. You have to take a step back and think about it a little differently than you're used to thinking.
yep.
Because
so
we're
that
so
is certainly the
fixated.
case.
We're so fixated on physical substantiality. We think things are physical. We think when we touch things and they provide feedback that they've been touched, we think, well, there must be physicality there.
Yeah, I think that makes perfect sense. You don't think that that's proper way of thinking?
It's the intuitive first reaction is, well, two things touching, they must be physical. But waves can interfere with each other, bounce off of each other, provide feedback from each other.
Now, generally
speaking, know that
waves
there are
pass
wave
straight
properties
through each other, so we don't generally see their effects
through each
so
other.
Hit something.
Depending on the nature of the medium.
No, that goes through each other no matter what the medium is. Two waves meet each other straight through every time.
Yes, if they're waves in the intuitive sense that we perceive waves, but we know that existence cannot be made out of waves and nothing but waves. Because if they were, there would be nothing to prevent all energy from leaving a given point instantaneously. So if existence was waves and nothing but waves, the sun would freeze instantly. All of the energy would dissipate. There'd be nothing to contain it. So we know that at some point in reality, there are physical, substantial particles. But our perceived particles, the electrons, whatever you think is physically substantial, takes up volume persistently, they cannot exist because they don't follow the rules of logic in terms of the way they act. They all have
I would agree with you there. Let me just make this point. You know, on this website, he's trying to say that an electron is basically a standing wave. Now, the rules of logic would indicate that in order to have a standing wave, there must be something for it to physically be standing in. So, for example, I'm a violinist, and you can set up this standing wave on the string, and that standing wave exists between the top nut of the violin and the bridge of the violin, and is actively driven by a bow. So if you tell me standing wave, then logically I think there must be a container to contain the standing wave. Now for an electron, I see no container. The electron stands in space on its own. There's no boundary. There's nothing that will say that you've got this wave in there that's either one wave, or there's two waves that fit in there, or three waves are standing in there. But logically, I think that there must be a container that defines the boundaries for where that standing wave is contained, and two, there must actually be a constant energy source in order to sustain that wave. Because standing waves, in order to sustain the standing wave, like if you're doing a standing wave on a rope, you have to continuously drive that wave in order to keep it standing, right? So that's a constant input of energy. So once again, logically, there must be, in order to maintain standing wave, must be some constant driver there. And for an electron, I see no such driver. So logically, I throw out the possibility that an electron can be any kind of standing wave, because A, there's nothing to contain the standing wave, and B, there's nothing to drive the standing wave. So therefore, a standing wave cannot exist. So that would be my argument.
The page that we're on mentioned de Broglie, and de Broglie worked with a gentleman named Bohm. De Broglie-Bohm came up with a theory that included group waves where there was smaller waves, but there was a attached larger wave. If you look up David Bohm book, you'll find a picture of the group wave I'm talking about.
That's not this. There's this other picture here. 3D attempt for de Broglie model by Kenneth Snelson. Is this close to what you're talking about?
No, hold on, and I'll confirm that I can get you to the exact right picture.
Yeah, if you can put it in the chat.
Because it attached, yeah, if you look up David Bohm books in Google and then go to images, the very first one shows a picture of his group wave theory that shows that there are a bunch of waves and there's a group that acts like a container, sort of.
Can you paste that into the chat so I can just click on it?
I didn't know I could do that.
Yeah, there's a chat window. There's a little balloon to chat.
I didn't know images worked.
Well, not images, but if you can send me a URL, then I can go to it. Otherwise, I'm sure I'm going to type in de Broglie or de Bohm wrong, and I'll never find it. Happy to do that. Like,
here it comes.
Yeah, here it comes. Type it in.
I see how this could work. There
okay,
you go.
So now I can click on that, and then we can go take a look at it right away. Okay, so let's see here.
His suggestion was that those smaller inner waves and the larger outer waves acted part and parcel with one another. And that's the root of his group wave theory, or pilot wave theory.
So how do you interpret this picture here? So this is like a sinusoidal wave where the amplitude increases and decreases. That's what I see.
Right.
So how does that correspond to anything that we know in atomic physics?
Well, that's at the heart of pilot wave theory, is that combination of individual wave plus group wave. And they're like locked together, part and parcel. And if you inflate that, you like add a dimension, that's flat, two-dimensional. If you inflate that, then you're going to get the shape that I propose is the physical medium that carries what you're talking about, everything, which is how you end up with the perception that something is spherical, but is carried by a toroidal medium. So you're looking for something that's toroidal and you're looking for something that's spherical, and I offer you a way of getting both.
I don't see anything toroidal in this shape, though. That's the part I don't understand.
Right. How to show you that? All right.
Plus, I mean,
stand by and I'll send you another picture.
This shows my two objections, which is that, you have what appears to be a standing wave, sinusoidal standing wave, but there's no reason for how this could actually be generated. I mean, how do you get a wave that is small in the beginning and then very highly amplified in the middle and then tiny going that, maybe this is like a radio wave. Maybe you can make a radio wave do this.
Right. There's another picture that'll show you what I mean by inflating and how it turns into the red-blue ball.
All right, you got some other pictures for me? Okay, let's see here.
That one's just a side-by-side of the red-blue ball and de Broglie-Bohm's group wave.
Okay, so your red and blue stripes just correspond to those to the maximum amplitude of those waves.
Right. It just adds a dimension. So it's like inflating the group wave from 2 dimensions to 3 dimensions.
So I can see that being spherical, but I still don't see the toroid part.
All right, so that red and blue shape, you can make it using your 2 hands by lining up your fingernails where the purple blur down that side is, with your thumbs together, and you'll approximate that
Thumbs
shape.
together? Like that?
No, line up your fingernails in a row,
Like this?
No, like a ball.
No?
Make a ball with your hands, as though you were holding a ball in your hands.
Like a ball? Like that?
Hold a single ball with both of your hands, with your
like
fingernails lined up.
Like that?
Yeah, getting close, but now put your fingernails in between each other so that they draw one line down the middle.
What?
Right now you've got your fingertips touching.
Yeah.
Instead, overlap your fingers slightly so that if you look down the row of your fingers, the fingernails are in a row.
You mean like this, on top of each other?
No.
No?
Shift one up slightly and one down slightly.
Like this?
All right.
You really got to get your camera working, I think. So I'm having difficulty following your instructions here.
All right, then excuse my messy hair. I'll turn on my camera. Give me if I look like a crazy man.
You'll probably do a better job than me.
All right.
Okay, there we go. We see
like
it.
that.
Okay.
All right, and then see how the thumbs how to show it like that.
Okay.
And see how the fingernails line up along the line of the purple blur on the side of the ball.
I see that, but I still don't see how that has anything to do with toroids.
Right. Now, take those 2 halves apart, flip one upside down, touch your thumbs, go like that, and instead of having a single group wave approximation, you now have a toroid.
But that's not your ball.
Right. It's my ball split in half of it flipped upside down and joined back together. Because when you're in amongst a field of them, the average, they're working left and right, left and right, left and right, left and right. So what passes through them is 2 halves of each one. The one it's coming from and the one it's going to. Again, I said you're going to have to manage to take a step back, flip your thinking, and imagine to see it passing through as opposed to being made of.
I don't know. That's kind of like asking me to dispel my a notion of logic.
Well, does anything about current physics make logical sense? Does wave particle duality make sense? That it's a particle, then a wave, then a particle, then a wave. Does that make sense?
No, but I think Newtonian physics seems to make a lot of sense. Whatever the initial stuff that.
Yes, because that's at a whole different scale than we're trying to talk about the nature of physical reality. We're not talking about things that are huge. We're talking about things that are tiny.
But I kind of think that Newtonian physics should apply to even things which are tiny. So I'd imagine if we had 2 electrons and we collided them into each other, that they would follow Newtonian physics. And you would see F equals ma, and you would see elastic collisions and things like that.
And things don't go through things.
I think we would see that as well.
Okay, so consider this. At our scale, there's friction. If there's a physical medium, be it perfect regular spheres or be it those bitoroidal group wave-like spheres that I propose, would there be friction? If there's friction in the medium at that scale, it binds. Even if it's perfect regular spheres, you have to dispense with friction, or else your medium can't operate. So you can't take everything.
Friction.
You can't take everything that exists at our scale and assume that it occurs at the lowest scale, because you know that friction cannot, unless you dispense with the medium and imagine that energy can have no container and just float around free by its own self, which makes no logical sense. So if you want physics to have any chance of being logical, you either going to have to imagine that things are held together by magic forces, or you're going to have to imagine that there's a physical medium. And if you imagine a physical medium, you have to recognize it cannot have friction or it will bind.
Well, I could believe that, because friction is a macroscopic effect due to collisions, which are
That's what I'm trying
Newtonian.
to point out, is that there are differences between the macroscopic scale and the sub-quanta or the sub-electron scale.
Well, I would argue oppositely. I would argue that no, there isn't any difference between those two levels. That Newtonian physics applies the same. It's just that when you get down to the subatomic level, there's nothing left there to cause friction. So therefore, it's frictionless. The friction only arises in large systems, but it's still fundamentally Newtonian mechanics. So on the most fundamental level, there is no difference. I mean, there may be a difference in behavior. There was just recently this argument in email that if you take two steel balls, you can collide them into each other. The steel balls end up being dented, but if we look at this with like two atoms of oxygen colliding each other, we say that collision is perfectly elastic. Now the thing is that the reason why the balls get dented, because of this gigantic conglomeration of trillions upon trillions of atoms, right? And you get that different behavior. But fundamentally, when the atoms of the metal ball, even when they collide together, the reaction is Newtonian and exactly identical to what happens in the oxygen case. So that there is no difference between the microscopic world and the macroscopic world. At least that's something I strive to do, which is to not make sure that there isn't any such difference.
I can only lead the horse to the water. I can't make people drink. You guys were talking about spherical standing waves and toroidal waves, and I'm trying to show you how, if the medium provides a toroid, then the wave going through the medium can be spherical, but still have the properties of toroidism as given to it by the toroidal-based medium that is traveling through.
That's certainly something we can consider. I'm not quite sure if I understand it.
What I was trying to offer, because you were having this discussion, spherical or toroidal. I'm saying, kind of like both, and in between.
Okay, well, good. So we have another viewpoint to consider. Although I was wondering, did you have any comments on my assertion, which is I don't believe in any of the standing wave stuff, because there's nothing to contain the standing wave and there's nothing driving the standing wave. I think that would apply directly to your model.
Yeah, I don't think anything is standing, because I think all of the particles of the medium are constantly in motion, and therefore anything that exists is going to be in motion except for relative to other things. And you can only have relatively standing. You can never have actual standing.
Well, then what's going on in Baum's picture here? That looks a heck of a lot like a standing wave to me.
His picture is a group wave as opposed to a standing wave. He doesn't claim that it's a standing wave. He claims that there's a larger amplitude, attached to the shorter amplitude. Maybe I'm getting the word wrong. The lower frequency is attached to the higher frequency.
I mean, honestly, this looks like an AM amplitude modulated wave, like radio wave. This is how they modulate the AM signal, and that you could, you would actually place an audio signal on top of the carrier wave, and the only difference is that it's modulated by amplitude. But I don't see how that could have anything to do with, say, particles. And that has to be deliberately driven, which is my second objection, that any wave kind of phenomenon has to be directly driven in order to sustain itself. And standing waves on their own are fundamentally not self-sustaining.
Yeah, I don't propose any standing wave. I propose that they're always in motion. That they decohere and cohere because they're going through a medium, so they come into and out of focus. And that's why we have the perception that they are wave particles, because when their particles are in focus, then they go out of focus and act like waves, then back into focus. But I don't know what the right words are to explain what I think I see. But I think if you look at
well, that's
well, looking further down your Glaze Labs research there, you just showed some of the hydrogen wave functions.
Yeah, we have this. He has a section on particles here.
The two basic
here in the middle of the screen here.
The two basic hydrogen wave functions are an E mode and a B mode wave. And if you take one of each and you merge them together, the shape that you get is the red-blue ball.
Well, your red-blue ball kind of looks like the last figure they have here.
All of those wave functions there can be derived by a medium that is made out of their root shapes, which are the E mode and B mode waves.
All right. Well, that's something to think about there. Let's go on here. So he's got all kinds of different theories here. So he's got one, it appears to have two different kinds of theories on gravity here. One is the electromagnetic radiation gravity theory. So this appears to be something where they say where the gravity is based on radiation pressure. It doesn't go that far into the explanation as to how this works. But that is one of the explanations of gravity here. But he does have another, I would say, competing theory for gravity here. And this is probably one of the pages which is most influential in my work, which is, does a nonlinear electric field gradient generate gravity? So the idea here is that the Earth is just this charged spherical ball. And so he has some specifications. So now these are things which are not terribly controversial. So the electric field strength at sea level is measured at about 120 volts per meter. So that's something that's measured. You can buy a meter that actually measures this stuff and called a field mill, and you can see that we live in a very strong electric field. So this is fact one. So we know we have an ionosphere about 50 kilometers above sea level, that the net Earth charge is like something to 10 to the 6 coulombs, that there's a voltage between the ground and the ionosphere of approximately 400 kilovolts. And so we see that the Earth is kind of this gigantic spherical capacitor. So that's one fact he points out, that we live on an Earth which has a very strong electric field. Now, the force that he talks about here, so there's this diagram here that if you have a dielectric object and you have a diverging electric field, that what happens is that, say in this case, this is a positive, on the left-hand side, there's a positive field. So if you have a dielectric object, which means its charges can be slightly separated, that will cause the negative charges to point towards the positive charge, which in this case would be left, and cause the positive charges to be repelled to the opposite side. Now what this does, because the negative charges are slightly closer to the attracting positive charge, that side of the object will be electrostatically attracted stronger than the repelling force it would feel from the positive charges, which are slightly further away. So you guys can kind of see how a dielectric object should behave in a region, in a diverging electric field here to cause an attractive force. And this is not, strictly the attraction of positive to negative, but rather it's just that the net forces acting on the dipole once the charges get separated is such that the particle does experience a force. So do people understand that concept? Because that's the number one thing you have to understand. Or do people disagree with that? That they think that you should not get a force. A dielectric should not feel a force in electric field. That's the first question. Do people understand that? Do they agree with that? So like, Bill, do you agree with that? Is this what happens?
If the dipole, multipole there is vibrating, it will produce the force of gravity, but if it's not vibrating, according to the laws of electrodynamics.
Well, I'm not talking about force of gravity. We're not talking about the force of gravity at this moment.
Right.
We're just talking about if you have an electric field and if you have a dipole particle, does it make sense that that dipole particle will be attracted to the source of the charge? That's what I'm asking. I'm not asking about gravity.
Yeah.
I'm talking electrostatic question.
You see, if that dipole, those charges are in an atom, there's other charges in the atom too that are closer, so they're going to dominate. And what happens is you have to have a vibration to get a net effect. If you don't have a vibration, you don't have a net effect.
Why would there need to be a vibration?
Because the rest of the local particles will dominate over the distant particle. In other words, you have to look at which is closer, which has more control. The atom has spherical symmetry. Can you change that spherical symmetry? And the answer seems to be no, because the things that are trying to change it are too far away.
Well, I think we're not talking about atoms here either. We're talking about a dielectric object.
Okay.
Now, basically everything, we're talking about like a substantial lump of matter. Like a pebble, right? And now what they're talking about here is you take a pebble and you expose it to a powerful electric charge, say coming off of a Van de Graaff generator. So let's just take that example. We have Van de Graaff generator. It's generating a very powerful diverging electric field. And we put a pebble in its presence. Now, what will happen is that the charges will separate in the pebble. The negative charges will move closer to the Van de Graaff generator. The positive charges will move further away, thus creating an unbalanced force, thus attracting the pebble. Do you think that would happen?
If the charges are moving.
Well, certainly the charges are somewhat mobile in any object.
Well, in my book, I calculated, and if they're not moving, there's no net force.
Well, what about this case? I mean, I'm showing you a picture here. I'm trying to whether you fundamentally agree or disagree
Well,
that here
you're assuming
there's no vibration.
you're assuming they can be static, but according to the laws of electrodynamics, if there's a net effect due to this dielectric object, you have to have some motion of the charge in each body.
Well, the motion that they're showing here is a migration of the negative charges to one side and the positive charges to the other, which is what you would expect
Well, but you
for an
see,
object exposed to an electric field of a certain polarity.
yeah, you see, if those where are those charges coming from? They're coming from atoms. What happens when you move something to one side of an atom? You can't just leave it stationary there. It's going to be trying to get back to where it came from, so it'll be vibrating. And so that vibration will always be there.
No, I mean, this is what we call inductive charging kind of thing. And this is certainly what happens with objects of a macroscopic scale. That if you go and you expose an object to a charge, you will see this migration of just the electrons. And that's really all that has to happen, is that the electrons will migrate to one side, thereby causing there to be this charge imbalance. And, you know, that's the only thing that has to move. There's no vibrations. There's nothing. And once that happens, then...
Steady. What keeps them steady? Because there's forces that want to vibrate, and you're saying, well, they don't exist. You're saying the electromagnetic force doesn't exist between these particles. But
no, they're doing that because they see this like gigantic, say, positive charge on the left-hand side of this picture here. So yeah, they're all going to go all the negative charges are going to migrate towards that left charge because of the electrostatic Coulomb attraction. And they're going to stay there as long as it sees this gigantic positive charge to the left. Now, the fact is, once that happens, then those negative charges will have a stronger electrostatic effect than the positive charges left on the other side, thereby creating a net force just by Coulomb's law, electrostatic law. Now, you have to understand it, because this is his main point here, that you can get this attraction on macroscopic objects without any vibrations, without there being any opposite charges. I mean, this dielectric object is not, say, net negative charged. I mean, that's the other way you could attract an object. If you charge it negatively and you put it next to a positive charge, obviously that would attract. But assuming that you don't allow the charges to escape and that it's still net neutral, like I said, if you have the Van de Graaff generator and you have a pebble and you turn the Van de Graaff generator on, should we expect that the pebble will be attracted to the Van de Graaff generator?
This may seem like a simple question, but it might not be. What's a charge? Where do charges come from?
Well, charges come from the action of electrons generally because they're immobile. And if you have an object and we call it, and if we say it has no charge, it's not because it doesn't have any charge. It's because it has balanced negative and positive charges. We believe the protons are positively charged and that the electrons are negatively charged. Now, when we say an object is charged, it means that there is an imbalance, that there is either more negative charges than positive charges, in which case we call that negatively charged.
That explains that we've observed a phenomena, but it doesn't explain what generates that phenomena. Do we just say, oh, charges, okay, sure, that sounds good, we'll go with that?
Well, then mainstream has really no explanation for that. But I would assert that we just need to, so at this point, we have to know what charges do. And electrons create what we know is a negative charge field. And protons create what we recognize as a positive charge field. That designation is somewhat arbitrary. Although if you're looking for an explanation for what those things actually are, my own theories indicate that the negative charge field is being generated by an electromagnetic wave of a specific phase. And the positive electric field is also being generated by exactly the same electromagnetic wave at the same frequency, but at opposite phases. And so that is why the electromagnetic field drops off as 1 over r squared. It does exactly the same thing as an electromagnetic wave because it is an electromagnetic wave. But, you know, that is my own speculation. You can take that or leave that. But for the purposes of this, of what's being said on this website, that's not material. The only thing that you have to believe in is Coulomb's law and the attraction of opposites. But I want to ask you, so do you think that this is true, that if you take any object, you place it in a high electric charge, like near a Van de Graaff generator, that it will literally be attracted?
At the macro level, yes.
I did some experiments on this, so maybe I'll show you my video here.
I don't agree with this concept of just making up a term and going, okay, that's good enough. We got a term. So, you know, like forces. Oh, well, we made up forces and they seem to match our observations. So let's just run with that. Forces, yay.
Well, I think that's okay. I mean, as long as what you're trying to explain doesn't go beyond that. If you're trying to
say that again.
If you're trying to explain why the pith ball is attracted to this other pith ball, then you can use Coulomb's law to describe that perfectly. And while we might not know what exactly the force is, if we're trying to describe, you know, why it's coming together, then I think that's still perfectly valid. But let me show you this experiment. So this experiment is going to show you that basically the electric field generates an attractive force to everything, okay? And they don't have to be charged, and they don't have to be vibrating, and they don't have to be anything. It's just an ordinary lumps of matter being attracted to something that has a charge source. So let me go ahead and show this experiment. And this is a neat little party trick that you can show people if you happen to have like a straw and a small bottle here. So what we have here is I have a straw and I just rubbed it in my hair to give it a charge, okay? So what I'm showing here is that that straw is creating an attractive force to anything that is placed next to it. So the force is symmetric, and so, you know, it's kind of hard to say whether is it a straw attracted to the hand or is the hand attracted to the straw. But the point is that if you have anything that has significant charge, it will attract any other bit of matter to it. So I showed that it attracts my hand. Now, if you think it's because there's a particular charging, I'm doing this with a metallic knife where the charges are highly mobile. And so the knife definitely is not charged, and it's made out of very different material. And so I'm showing it's being attracted to glass. And the electrons in a glass are highly immobile. So it's attracted to the wood. And it's attracted to the garlic salt. It's basically attracted to everything. So this is a force that definitely experimentally exists. There's this attractive force that's not having anything to do with, that doesn't have anything to do with opposite charges. So now I'm going to do the opposite experiment here, where I'm going to start with the uncharged knife, and I'm going to pull it around using the charged object, which is going to be a comb, which I can charge it pretty high. The depth comb, that knife is neutrally, and I can drag it around with a comb. You can see how the comb can attract that neutrally charged chunk of metal. And I replaced the material with wood, which is not a good conductor. So it's not like it can charge. It can get inductive charging. And you can see how strongly attracted that wood is to the charge comb. So it works on practically anything. It doesn't matter what it is. Does not seem to matter at all what kind of material it is. But I put that up as a demonstration of this particular effect. Because what this website is saying is that gravity is actually that effect that you saw in the video. So you guys have any comments on that video? Do you think that was a fake video? Or are you impressed that everything is attracted to an electrostatic source?
Franklin?
Yes.
Gravity cannot be shielded, but the electromagnetic force that you're using can. So what do you say about that?
Well, the question is, can it? I mean, I would say that the thing is that it's very difficult for us to generate an electric field, say, the size of the Earth. And I would assert that the problem here is that we can shield relatively small, localized charges. Like if I stuck that comb inside of a can, it would be shielded. But when we get something the size of the Earth, which is like 10 to the 6, coulombs, compromising, hundreds of, perhaps millions of volts, that at some point your shielding material has to be saturated. I mean, a thin tin can must have some limits to how much it can shield. I mean, can a thin tin can shield the electrostatic effect from the entire planet Earth and its field? Or is that field so strong that it's going to turn the atoms in that can such that that field passes straight through? So that is kind of, I mean, that's not scientific, but my answer to that objection is that on anything on an earthly scale, we cannot shield it against because all the materials on Earth would be completely saturated and basically would present no problem for the field of the magnitude of the Earth to get through. It's just saturated. So, but but I still want to see whether you're impressed by the fact that there is definitely this undeniable attractive force of neutrally charged objects to charged object, because that is the key to what's being explained on this website. Anybody else think that was fake news? Because it really isn't. There's nothing fake about that. That's exactly what happens. But if you assume that kind of force exists, now he does go through and he does do some math here, and this force does have a name in the mainstream. It's called the dielectrophoritic force, and in it there's this fairly simple formula here, which describes the magnitude of that force. So the equation is F equals 1/2. This first symbol is this fancy A is the effective polarizability of the object, and that's just an expression of how the object reacts to an electric field, how strongly its dipoles react, times the volume. And then we have the del operator, which has to do with a divergent field, and the divergent field being described by E squared, okay? So fairly simple formula. It actually looks an awful lot like kinetic energy formula, 1/2 mv squared. That's basically what we have here. We have something which is dependent upon the polarizability and upon the volume. So as a bit of research on this, I tried to calculate, okay, assuming that that formula is correct and that this force definitely exists, and what it is normally used for is to separate out microparticles. Like if you have it's usually used in medicine where you have a bunch of organic molecules and you want to separate them. If you put them in a diverging electric field, because the polarizability on these different micros things are different, they will pull it in with a different force, and you can actually separate things. Okay, so that is the usual use of this law, and so we see a lot of research on this concerning particular shapes, whether they're rods or spheres. And so that's what this second formula here, that this has to deal with specifically whether it was a sphere or not. But what I did was, presuming that this formula is correct, now we can plug this in. So this is a simplification of the formula, which is force equals 1/2 times the polarizability times the volume times the electric field divergence squared. So I wanted to find out, well, if this is true, then how much force should I expect there to be on, say, my human body of around 150 pounds? So people are mostly water, and we can look up the effective polarizability of water, which is 1.45. So we have that number. I have the reference for that polarizability of water. And we can find out what the average volume of a human is, which is 0.07 meters cubed. And I have a reference for that. So we know what the polarizability of water is. We know what the average volume of a person is. So we plug that into the dielectrophoresis formula, and we find out that a body of water of that volume should be attracted to the Earth with 730.8 newtons. And if you translate that into pounds, yeah, that's like about 150 pounds. So this is the curious thing, is that if we think this formula is correct, and if we think that the electric field measurement of 120 volts per meter is correct, and we just simply plug the known values for water, we find that the force we expect pretty much accounts for the force of gravity. So I think that this is a particularly strong argument because, unless, one of these, you would have to argue that this formula either doesn't apply, or that I have the calculations wrong, or that the inputs for this formula are incorrect. But otherwise, if this is correct, then even if gravity is something else, let's suppose gravity is like a pushing force due to things coming down to our heads, then you would have to also account for the fact that of my body weight, which is about 150 pounds, about 150 pounds of it would be accounted for just because I'm sitting in an electric field of 120 volts per meter. Right? Now you can have all kinds of objections to, that being the source of gravity. For example, the shielding and, should things weigh differently? Would the force be 1/r²? I mean, you can have all kinds of objections like that. But if it turns out that the calculated force of this glass of water turns out to be the observed force of gravity, then you would have to say that, I think you would have to say that it must be gravity, and that every single other objection you could lodge against that is irrelevant because it already accounts for the vast majority of the observed weight.
So Franklin, are you suggesting that if we had a very large parallel plate capacitor, which is charged at minus 120 volts per meter, and you walked into it, you would be weightless?
You would have to create a field that exactly opposite of the Earth, which means you would have to create that. You couldn't create that with just a sphere with an electrostatic plate. You would actually have to get another body the size of the Earth to generate that field. But theoretically, yes, if you manage to create something that has an effective, 10 to the 6 Coulomb charge, effective like 3,000 miles away or 1,500 miles away for the radius of the Earth, then yes, you would go weightless. I mean, I would think that, that would be obvious that if you put something the size of the Earth next to us, that if we were right between that yeah, we would go totally weightless.
Why the size of the Earth? You say 120 volts per meter. Let's say that you're 2 meters. So 2 meters would be what? 240 volts. I mean, 240 volts between the plates is nothing.
That's a divergence. That means it's diverging by 120 volts per meter. I mean, the actual voltage you're sitting on.
Okay.
And the only thing that really matters here is actually the divergence.
Okay.
The calculations show that if the Earth were actually like a flat plate, that actually there would be no attractive force. The divergent forces actually, the asymmetric forces only appear in a spherical object. Actually, one of the interesting things. But once again, this is one of those objections where I would say, so what? Because it's like, yeah, you can come up with those objections and you think that, well, if I stuck a plate above my head, that exactly cancels the 120 volts per meter, which I would agree you can do. But that still doesn't defeat the logic that says that no matter what, that 150 pounds of my 150-pound weight is accounted for by just sitting in this electric field by this formula. I mean, I just demonstrated to you for a fact that if you have an electric charge, everything is attracted to that charged object, right? So the Earth is for sure a charged object. So for sure, if you believe anything that you saw in that video, all neutrally charged objects will be attracted to it, just like I showed the knife being attracted to the straw or the straw being attracted to the wood. Just everything is attracted to any charged source. So even if you think gravity is something else, like I said, pick any theory you want. At least some of the force that we feel must be from that electrostatic attraction. It just has to be. I mean, how could it not be? How could we not be sitting on a charged ball and then not be attracted to it?
Franklin?
Yes. Mm-hmm.
I just posted a picture at the bottom of the chat window there. Can you pull it up?
Uh-huh. Yeah, let's see what you get.
It's a picture of Earth's gravitational anomaly pattern.
Mm-hmm.
And
so what is this showing here?
If you look at it, you can see that it's an interference pattern, that gravity interferes with itself.
Are you sure? Let's see. So what's the green and what's the white?
Green is a positive gravitational anomaly.
Time?
Green is a positive gravitational anomaly, and gray is a negative gravitational anomaly, as measured by the Grace mission, which is a pair of satellites which circle the Earth constantly measuring how strong each region of Earth's gravitational field is. Mm-hmm. And then they weigh them against each pass. It weighs it against itself. And so it shows where gravity has gotten stronger and weaker from one period of time to the next period of time.
How can they tell that? I mean, why is this? Is this during the time the satellite has been orbiting, or what?
It's actually a pair of satellites. And what happens is that they are very accurately measured, the distance between them. They chase one another and they're identical. They're twin satellites. And when one approaches a stronger area of gravity, because it's in the lead, it realizes that extra pull first, and it moves farther ahead from the other satellite. So they measure the distance between the two, and those 200 kilometers become 200 kilometers plus a couple of meters or whatever. I don't know how much the distance fluctuates. Then when the second one approaches that same extra pull, it starts to accelerate. When the first one passes that extra pull, because it's in the lead, it decelerates first, and then the second one catches up to it. And so they constantly circle the Earth.
How it measures this, although you're saying that they're finding these stripes of stronger and weaker gravity, although I still don't understand, that they have time, which is 2000.29, and then 25 kilometers, and it's like, why they just mix together every single dimension possible here. They've got millimeters, they've got time, they've got, what does that mean?
Hold on, and I'll put a link to a video, and it'll explain it a little better, because you'll see how it changes over time.
Well, that's interesting, but what does that have to do with our discussion here about, the website is saying that gravity is an electrostatic effect. So you're just showing that there are some gravity anomalies, and that's very interesting. But
I'm showing that it interferes with itself. Gravity interferes with itself. So you're trying to determine what the nature of gravity is. I'm showing you that it's bidirectional and it interferes with itself. If you want to pull up that video.
Does that support or reject this hypothesis that gravity is caused by this diverging electric field?
Supports, I believe.
Supports. Okay, I'm thinking about it because this is the first time I've seen this data.
Take a look at the video, because it'll explain it a lot better. Instead of being a snapshot, you'll see the changes in Earth over time. Where it shows the date, where it says like 2002.09, that 0.09 is 9/100ths of a year. So it's basically showing you almost like weeks. But anyways, like I said, the video is short, and you don't have to watch the whole thing. Just watch 10 seconds of it, and you'll get the idea that these are gravitational anomaly pattern, and it fluctuates, it moves around.
So this is the video here?
Yeah.
All right, so we'll watch this. So, and so far, okay, so there's the fluctuation we're seeing there, which is interesting.
Because something else that is very noticeable in the video, if you compare it, is that if you see Greenland acts differently than the rest of the world. Because it's closest to the North Pole, it actually fluctuates with a frequency of 11.5 years, whereas the rest of the continents are fluctuating on an annual seasonal basis. Greenland, the anomaly pattern of Greenland goes up and down like the middle of a trampoline, in conjunction with the polarity and the magnetic strength of the sun's magnetic field. When the sun's magnetic field is north-south, Greenland will be green in the center and gray at the outside. When the sun flips and goes south-north, Greenland shows the exact invert pattern.
Well, that might be interesting, because if you think that the gravity is being caused by the electric field, you would think that, yeah, the electric field would certainly be influenced by what's going on with the sun, which is constantly trying to blow that electric field around. So that would be an interesting bit of data that might support this idea that gravity is being caused by an electric field if its influence, you can clearly see its influence from the sun.
Yes. It
so that's
shows
very interesting.
A direct relationship between magnetism and gravity. We already know that, because if you put magnets opposite pole on top of each other, they defy gravity. So we know there is a relationship, but this shows it in a whole different light.
All right, well, that's very interesting. So thank you for bringing that. But it looks like we're getting towards the end here. Although I wanted to give Bill a chance to respond to this assertion. So, Bill, how would you deal with this seeming fact that all matter is attracted to a charged ball and the Earth is a charged ball? Therefore, at least some of what we experience as gravity has to be due to that effect.
Well, as I say, if you take the laws of electrodynamics and you calculate the force, if there's no vibration, they cancel out.
Then how do you explain that video that I showed where everything was attracted to the straw?
Because there is a vibration. You don't think there is, but there is. And that vibration, and if you change the temperature, you'll discover a temperature dependence because the vibration will be larger at higher temperature and smaller at lower temperature. And so you'll see an increase in the force of gravity with temperature. And the Russians have measured that with using...
Yeah, but how do you deal with the fact that of the 150 pounds of my weight, 150 pounds of it is already accounted for by the electric field?
That calculation is kind of crude. I don't think it's... you should do it on something that's more well-defined, like a steel ball or something like that. And then you would find that there's a temperature dependence to it. There's a lot of other factors that don't agree with that approach. So I think you need to look at those things. And many laboratories have confirmed the Russian data that there's a temperature dependence to gravity.
Yeah, but that's a very, very fine difference here. The thing is that if this is true, then even if you think that gravity is due to your vibrating dipoles, they would only have to account for like 1% of the actual gravity effect, since the other 99% is accounted for just from the diverging field.
But you see, if you take the laws of electrodynamics, if you assume they're true, then you won't be able to satisfy
all. But if you take the laws of common sense and you have an experiment showing that all objects are attracted to a source of charge, and you establish that the Earth is a charged object, then logic would demand that all objects on the Earth be attracted to its surface, period, right? By the laws of logic.
Well, but you see, you haven't looked at the charges. You don't know what they're doing.
We don't have to know what they're doing. We just experimentally observe that all objects are attracted to a source of charge. Empirically, that's what happens.
But we can perform an experiment where we let the charge vibrate and where it's not vibrating and you don't get any force of gravity.
We're not talking about force of gravity. We're talking about this force observed.
That's
but
right.
In any case, I'm actually out of time. I have a hard stop today. But that's just something for you to think about.
Okay.
That just think about the experiment I showed in the video, saying, okay, yeah, this definitely happens. And they establish the fact that the Earth is charged, which it definitely is. So put those two together and see, and use logic and see what you come up with. Okay, but I think that does it for this week. So I'm going to be doing some work on easy talks and see whether we can establish the talk next week using that. But definitely by August we'll be switched over. But for today, that's our talk. And I would invite you to go ahead and look at glazelabs.com more closely. There's, like I said, we've only touched on just a very few of the topics that are on his website, and I think it's been very influential to me itself. But until next week, we'll be signing off. Thank you.
Thanks for your time, Franklin.